We have finished the theoretical part of this chapter, and that was section A, correct. Now, we begin another section, that is section B, for all the illustrative numericals given in the textbook. Okay, fine. Here I have written section B, that is illustrative numericals, and you know the symbol for illustrative numerical, we are using this symbol IN, illustrative numerical. Okay. Kindly read now statement of first illustrative numerical on the screen. Have you read it? Look, we are given this formula for current passing through a given conducting wire. What is that formula? I equals to I0 plus alpha into T. Fine. I0 is some constant, they have given 10 ampere. Alpha is also some constant, they have given with the value 4 ampere per second. Unit of alpha is ampere per second, unit of T will be second, second will cancel, giving you ampere, ampere plus ampere will be ampere, that is why unit of current is here ampere. Okay, fine. Now, what have they asked? If this is the current whose dependence on time is like this, then what will be the total amount of electric charge passing through the cross section of that wire? That is what we have to find out. But of course, in first 10 seconds, what have they said in the statement? In first 10 seconds, let us find out that total quantity of electric charge. See, this current depends on time, correct? Means as time will change, this amount of current will change. So, right now current is not constant. If current is constant, then only you can apply formula I equals to Q upon T. But here current is not constant. So, you cannot apply the formula I equals to Q upon T. No, in that case you must use this formula I equals to dq upon dt, correct? I equals to dq upon dt, fine. Now, transfer this dt over here, come on, dq will be 10 into dt plus 4 into t, just put it in bracket, into dt, correct? Now, what is this? Partial amount of electric charge, and now we require total amount of electric charge. Naturally, we should add the partial values of electric charge, and for that mathematically we should go for taking integration. Come on, take integration on both the sides. Integration dq, come on right hand side, 10 is constant, integration 1 dt, correct, plus 4 is constant, integration t dt, but they have asked total amount of electric charge in first 10 seconds. In first 10 seconds means in the time interval from 0 to 10 seconds. In the time interval from 0 to 10 seconds, and you know the lower limit of integration is the smallest value of variable and upper limit of integration is highest value of variable, correct? Here lower limit is 0, upper limit is 10 seconds, got it? If they ask find out total electric charge passing through the cross section of that conducting wire, say from 15 to 25 seconds, suppose, then you may write here 15 and here you may write 25, got it? But here they have asked only for first 10 seconds, that is why the limits are from 0 to 10, from 0 to 10, got it? Summation of partial values of electric charge will give you total amount of electric charge, okay? Let it be capital Q. Now, this 10 as it is, integration 1 dt is nothing but t, okay, from 0 to 10, from 0 to 10. 4 as it is, integration t dt, it is t square by 2, correct, from 0 to 10, 0 to 10. Have you remembered that formula? Integration t raised to n dt will be t raised to n plus 1 upon n plus 1. Here you can say t raised to 1. So, what will be result after integration? T raised to 1 plus 1 upon 1 plus 1. that is T raised to 2 upon 2, correct? Here it is T raised to 2 upon 2, got it? Now 10 as it is. Now instead of this variable, we are supposed to put upper limit first of all, and then after putting minus sign, we should put the lower limit. Come on, instead of T we should write 10, after putting minus sign, instead of T we should write lower limit, that is 0, plus 4 as it is. Instead of T, when I write upper limit, that is 10, it will be 10 square upon 2, 10 square upon 2. After putting minus sign, we are supposed to write the lower limit, which is right now 0, 0 square will be 0, 0 upon 2 will be 0, correct? Simplify, 10 into 10, 100, here it is 10 square upon 2, that is 100 upon 2, that is 50, 50 fours are 200, 200 plus 100, that is 300. What is SI unit of electric charge? Coulomb. Write symbol capital C and don't put any full stop, okay? Leave some proper gap over here, write capital C and don't put any full stop. But mind well, this is the total charge flowing through the cross section of that conducting wire, in which current depends on time according to this formula, but only in first 10 seconds, only in first 10 seconds, okay? If they ask another interval, then accordingly you can decide the limits of integration and you can find out the new answer, correct? Now kindly read this statement for illustrative numerical number 2. Read it? Look, they have given two wires connected one after another of different cross sectional area. First wire is made up of copper, let it be wire number 1. Second wire is made up of iron, let it be wire number 2. Okay? Copper wire has got smaller cross sectional area and iron wire has got bigger cross sectional area, okay? And tell me, here when the wires are connected one after another, means they are connected in series. And don't you know, for the components connected in series, current passing through each component would be same, and that same amount of electric current I have shown by symbol capital I, okay? That same current they have given with value 8 ampere in the statement, okay? What we have to find out here? Electric current density in both the wires. Let us find out. For copper wire, come on, recall the formula, J equals to I upon A. How? See, whenever considered surface is planar surface, perpendicular to direction of flow of electric current, and the value of electric current density is same at all the points on that planar cross section, then the formula for current passing through that cross section was, we had studied in theoretical part of this chapter, I equals to JA. Remembered? I equals to JA. IJA. Remembered? I equals to J into A. From that you can find out J, it will be I upon A. J equals to I upon A. Correct? But right now you are talking about copper wire, which is first wire. So here I am writing J1, here I am writing A1. Correct? Current is same. Current is same. Don't write I1, I2. Got it? What is A1? It is the cross sectional area of first wire. And when you take cross section here, it is circular. For any circular cross section, what is the area? Pi into radius square. But radius is diameter upon 2. So pi into d by 2 whole square will be pi d square upon 4. Pi d square upon 4. So remember, cross sectional area for a circular cross section in the terms of diameter, it is pi d square upon 4, pi d square upon 4. So this A1 is pi d1 square upon 4. Denominator's denominator will become numerator, correct? And here I am writing d1, that is diameter of circular cross section of first wire. Got it? 4 as it is. What about this current? They have given 8 ampere, pi value is 3.14. d1 is diameter of circular cross section of copper wire. They have given 0.2 millimeter, converted into meter, multiplied by 10 raised to -3, and then don't forget to make it squared. Okay. Simplify, answer is 2.5 into 10 raised to 8, that many ampere upon meter square, because SI unit of current would be ampere, for cross section area it is meter square. So SI unit of electric current density is ampere upon meter square. We have studied in theory, correct? Ampere upon meter square, or you may write ampere into meter raised to minus 2, ampere into meter raised to minus 2, but don't put any full stop here. Okay. Now similarly for iron wire, come on, because it is second wire, you can write here J2 and here A2, then J2 will be I upon A2, but what is A2? It is the circular cross section area of second wire, it is pi d2 square upon 4, pi d2 square upon 4, denominator will become numerator, correct? Put up the values, 4 as it is. What about current through this iron wire? Current through both the wires right now it is same, it is 8 ampere, it is 8 ampere. Pi is 3.14, this is the diameter of circular cross section of second wire, that is for wire of iron, that they have given 5 millimeter, converted into meter, multiplied 10 raised to minus 3 whole square. Simplify, answer is 4.07 into 10 raised to 8, that many ampere upon meter square. Got it? Fine. So this is how we can find out electric current density using this formula. Got it? Come on my dears, now read the statement for third illustrative numerical. It is a very good result. Read it? Look, we are given a solid cylinder, cylindrical conductor whose radius is capital R, in which the electric current density is J equals to J0 into bracket 1 minus small r square upon capital R square, where small r is the perpendicular distance from its axis. Correct? If electric current density is given by this formula, then we are asked to find out total electric current passing through this entire cross section of this cylindrical conductor. Okay? How to find? I am showing you. Tell me, here current is flowing parallel to the axis, okay, and we take electric current density vector always in the direction of electric current. Okay, fine. Now we want total current passing through this entire cross section of this cylindrical conductor. For that you just do one thing, this entire circular cross sectional area you just divide into very large number of extremely thin concentric circular rings like this. Say this is very first ring, very small, exactly at the axis, here only at the center, and then after you can think of another very thin circular ring, then third, then fourth, then fifth, and so on, correct? So if this entire area is divided into such extremely large number of extremely thin concentric circular rings, then out of such many rings, I am just showing here in the figure one ring as a specimen. Okay? So this is highlighted ring which I am considering as a specimen, as a sample, for which the inner radius is small r, correct, and outer radius is this much. If this thickness is dr, then this outer radius will be r plus dr. Here I have written r plus dr, correct. Now tell me, because you have considered here area only for this specimen circular ring, which is a very small part of this total area, then its corresponding area vector we should write by symbol vector dA, correct. This is the surface element, and for that surface element this is the surface area vector. Okay, fine. Now that area vector, you know, it is to be drawn always perpendicular to the plane of surface element. Surface element is having plane like this, vertical plane, and perpendicular to that will be horizontal. So vector dA is like this, horizontal, fine. And you can see in the diagram now, vector j and vector dA, both of them point in the same direction. And when they point in the same direction, angle between them will be 0 degree, okay, fine. Right now we are considering very small part of this entire cross section. So whatever amount of electric current is passing through this surface element, that symbol I am giving dI, that is partial current, and according to formula, this partial current you can always write vector j dot vector dA, that is dot product between electric current density vector and area vector, got it? dI as it is, vector j dot vector dA means what? J dA cos theta, that's what I have written here, J dA cos theta. Now this dI as it is, what about J formula? Electric current density at perpendicular distance r from the axis is given by this formula, which is given to you in the statement. J equals to J0 into bracket 1 minus small r square upon capital R square. Same formula written here, J equals to J0 into bracket 1 minus small r square upon capital R square, correct? What about dA? dA is the area of this extremely thin circular ring. Remember formula for area of extremely thin circular ring, it is circumference multiplied by thickness. Circumference of a circle with radius r, what is it? 2 pi r into thickness is this much, which is right now dr, correct? So what is dA formula right now? Circumference into thickness means right now 2 pi r dr. So dA is 2 pi r dr. What about theta? Theta is angle between these two vectors. I told you earlier, because they point in the same direction, angle between them is 0 degree, correct? Now just multiply 2 pi over here, so it is 2 pi J0, multiply small r inside the bracket, r into 1, that is r into r square will be r cube upon capital R square as it is, dr as it is, and cos 0 is 1, okay? I want total current passing through this entire cross section, for which I must take the summation of partial values of electric currents. Just to find out the summation mathematically, what we do, we just go for taking integration. So take integration on both the sides. Integration di, here it is, integration di. Now this 2 pi J0 is constant, taken out. Now integration in this part, that is integration r dr, look here, integration r dr, correct? Minus 1 upon capital R square is constant, minus 1 upon capital R square is constant. Now integration r cube dr, integration r cube dr, here it is, integration r cube dr, got it? What about the limits of integration? I have told you many times, lower limit of integration means smallest value of variable, and upper limit of integration means highest value of variable, correct? Here this small r is variable, whose smallest value will be on the axis, that is small r equal to 0, that is the smallest value, that's why it is lower limit now. And when you take the ring, the biggest ring inside this cylindrical conductor, then its radius will be this much, which is also radius of cylindrical conductor, that is capital R. So maximum value of small r will be on the wall of the cylindrical conductor, which will be equal to capital R. So maximum value of variable is capital R, that's why it is right now upper limit. I repeat for the last time, lower limit means the smallest value of variable, upper limit means highest value of variable, correct? Fine. Now summation of partial values of electric currents will give you total current, that is capital I, 2 pi J0 as it is, integration r dr, according to formula it is r square by 2, from 0 to capital R, correct? Come on, minus 1 upon r square as it is, integration r cube dr, it is r raised to 4 upon 4. R raised to 4 upon 4, again limits are from 0 to capital R, 0 to capital R. Got it? Now this part as it is, come on, instead of small r, when you write capital R, it is r square by 2. After putting minus sign, put the lower limit, instead of small r, write 0. 0 square is 0, upon 2 will be 0. Minus 1 upon r square as it is, instead of small r, write capital R raised to 4 upon 4. After putting minus sign, put the lower limit, that is in place of small r, you should write 0. 0 raised to 4, 0. 0 upon 4 is 0. Simplify now. 2 pi j 0 as it is. This is r square by 2, I am writing as it is. Minus r raised to 4 upon r square. So left is r square in the numerator upon 4. Minus r square upon 4. Now 2 pi j 0 as it is. R square upon 2 minus r square upon 4 is r square upon 4. 2 2s are 4. So it is finally pi j 0 r square upon 2. Pi j 0 r square upon 2. Correct? So this is the total current passing through this entire cross section, provided electric current density is given by this formula. Correct? Now in examination, you might be given these two values directly, and you might be asked to find out numerical value of this total current. So remember this formula also. Okay? What is J0? I repeat once again. According to this formula, it is nothing but maximum current density, which is electric current density at the axis of the cylindrical conductor. What is capital R? You know, it is the radius of the cylindrical conductor. Okay? If you are given these two values, you can use this formula to find out this total current in ampere. Got it? Read now statement of fourth example. Read it? Look. Here we are given some specific shaped conductor. That specific shape I have shown in the figure, in which on the left side we find two wires of same cross sectional area. On the right side we find three wires of same cross sectional area. Compared to this wire, you can see this wire is rather thicker, and that's why that thick wire I just indicate by symbol 1, that is first wire, and this thin wire I just indicate by symbol 2, that is second wire. Okay? Thick wire we take wire number 1, thin wire we take wire number 2. Okay? Now we have to find out drift velocity of free electrons in both the wires, that is in thick wire also and in thin wire also. Let us recall this formula which we have studied in theoretical part of this chapter. I equals to A, Vd and E. Give me identification of E symbol. This is electric current, this is cross sectional area, this is drift velocity of free electrons. What is small n? Number of free electrons per unit volume of the wire, that is free electron number density. Its unit is free electron per meter cube. And what about small e? It is magnitude of charge of one electron. Got it? Find out Vd from here. Transfer this A and E in the denominator on left side. Vd will be I upon A and E. I upon A and E. But what is the circular cross section area in terms of diameter? Pi d square upon 4. So capital A is pi d square upon 4 will go up. Right? So it is now 4I upon pi d square and E. Give it equation number 1. Now first of all, let us talk about thick wire, that is wire number 1. So just use the symbol here Vd1, here I1, here D1. Okay? So Vd1 will be 4 into I1 upon pi D1 square and E. Come on, pi D1 square and E. Correct? Why not N1 here? Because the material of the wire is remaining same. They have given copper wire. Correct? As long as the material remains same, the free electron number density would remain same. Okay? So whether you consider this thick wire or thin wire, N remains constant. Okay? Don't write N1, N2. Got it? And what about small e? It is magnitude of charge of one electron, it is already constant. Put up the values, 4 as it is. What about current through the thick wire? Current through thick wire, they have given 3 ampere, correct? Fine. Now here you can consider some junction where these two currents will add up. So 3 plus 3, that is 6 ampere. But further, the total 6 ampere current will be divided into that many parts equal to number of branches. Number of branches is 3. So it will be divided into 3 parts. But each branch is having same cross sectional area. So that total current 6 ampere will be divided into 3 equal parts. 6 upon 3, that is 2 ampere each. Okay. So what we can see in the diagram, current passing through thicker wire is 3 ampere, current passing through thinner wire is 2 ampere. Got it? Fine. Right now we are talking about thick wire, correct? That is wire number 1. And through the thick wire, what is the current? It is 3 ampere. Okay. So just put I1 equal to 3. Pi value is 3.14. What is D1? Diameter of circular cross section area of thick wire, which they have given 0.2 centimeter. Convert it into meter. Multiply 10 raised to minus 2. Make it a square. What about N? Free electron number density in copper, they have given in the statement 7 into 10 raised to 28. That many free electron per meter cube. I am writing same value, 7 into 10 raised to 28. What about E? Magnitude of charge of 1 electron, 1.6 into 10 raised to minus 19 coulomb. Still this factor is to be multiplied here. Okay, I written here with multiplication sign, this value I written. Now simplify this, and the final answer is 8.5 into 10 raised to minus 5. SI unit of velocity is meter per second. Meter per second. Okay, but this is for thick wire. What about thin wire? Let it be wire number 2. Then instead of VD1, you may write VD2. Instead of I1, you may write I2. Instead of D1, you may write D2. Put up the values for thin wire. 4 as it is. Current passing through thin wire is 2 ampere now. So it is 2 ampere. Pi value is 3.14. What is D2? Diameter of circular cross section of thin wire. Diameter of circular cross section of thin wire is 0.1 centimeter. 0.1 centimeter. Convert it into meter. Multiply it to minus 2. Don't forget to make it square. Okay. What about N? Free electron number density. That is number of free electrons per unit volume of this copper wire. They have given 7 into 10 raised to 28 free electron per meter cube. So value of N is 7 into 10 raised to 28 free electron per meter cube. Magnitude of charge of 1 electron, 1.6 into 10 raised to minus 19 coulomb. Same value are written here. Simplify. Final answer is 2.3 into 10 raised to minus 4. SI unit of velocity is meter per second. Got it? Fine. Now read now statement for illustrative numerical number 5. Read it? Come on. What have they said in the statement? Length of one metallic wire is increased by 0.1 percentage. Then what is percentage increase in its resistance? That is what we have to find out. Okay. My dears, here please remember the method which they have given in the textbook is not universal method, is not general method. It is the method which is to be applied only in case when increase in the length is very small. So that method, which is the method of derivative, is having one limitation. You can use it only for very small changes in the length. Okay? But if change in the length is very large, then you cannot apply that method. Okay? So that method is not a general method. Here I am showing you that method which is most general, and you can apply it any time. I mean, for very small changes in the length, for very big changes in the length, no problem. Moreover, Using that method which is given in the textbook, you will get some approximate answer. But here final answer will be most accurate. I just suggest and appeal to everybody, please follow this method. Okay, fine. What is the formula for resistance of a conducting wire, of a metallic wire? It is given by this formula, R equals to rho into L by A, where rho is resistivity or specific resistance. Remembered? L is the length of that wire, A is the cross sectional area. Just multiply by L, numerator and denominator, then it will be L into L, that is L square, and here when you multiply by L, it is A into L. Now this rho as it is, L square as it is. What do you mean by A into L? A into L means, look here, this cross sectional area multiply by this length. If it is not informed to you that wire is cylindrical, by default you should take that wire cylindrical only. And for any cylindrical wire, this cross sectional area into length will give you its total volume. So this A into L will give me volume of that wire, let it be capital V. Okay, fine. Now tell me, whenever you stretch any wire, the type of material remains same. If it is copper, it will remain copper only, and when type of material does not change, naturally resistivity can be taken constant. So rho is constant, correct? And whenever you stretch any wire, its volume will remain constant. You know why? You will answer that when we stretch the wire, length will increase and the wire will become thinner, so cross section area will decrease. My dears, when this increases and this decreases accordingly, then this multiplication will remain constant, that is volume will remain constant. But that argument is not proper. Proper argument is this, you know, density equals to mass upon volume. Density equals to mass upon volume. When you are stretching any wire, material remains same, so density is constant. When you stretch the wire, neither you are removing any mass out of that, nor you are adding some mass to that, so naturally mass is also constant. Density equals to mass upon volume, density is constant, mass is constant, so volume has to be constant. That's why here volume will remain constant. When rho is also constant, volume is also constant, then remove this constant part, then you can write R proportional to L square. When you remove this constant part, R proportional to L square, R proportional to L square. Okay? Then you will ask me, sir, we have studied in theoretical part that R proportional to L. That is also true and this is also true, because when I taught you about R proportional to L, at that time I told you that cross section area is to be kept constant. If cross section area is constant, then R proportional to L. But here when you stretch the wire, wire will become thinner, cross section area is not going to remain constant, here volume will remain constant. At that time R is not proportional to L, but R is proportional to L square. Okay? If cross section area is constant, R proportional to L. If volume is constant, then R proportional to L square. Correct? Now onwards, you please remember, whenever they talk about stretching any wire uniformly, please remember that R is proportional to L square. Okay? And if it is a relation of direct proportionality, then can't you write 1, 2, 1, 2? Yes, we can write R1 upon R2 will be equal to L1 square upon L2 square. Here it is. R1 upon R2 equals to L1 square upon L2 square. Correct? Fine. Now whenever they talk about some change in terms of percentage, you please take initial value to be 100 units for your ease in the calculation. Okay? Here they have talked about increasing the length by 0.1%, then you please take original length to be 100 units. So original length is L1, that's what I am assuming here. If L1 is 100 units, if L1 is 100 unit, then what about new length? You know they have given that length is increased by 0.1%, then naturally final length will be 100.1, 100.1. How? See, in order to find out the percentage easily, we are assuming original value to be 100 units. What is 0.1% of 100? It is 0.1, but that much is the increase. So 100 plus 0.1, that is 100.1. Correct? Suppose they give length is increased by 5%, then what is 5% of 100 units? It is 5 units, and that much is increased. So 100 plus 5, it will be 105. If they give 15% increase in the length, Then what is 15% of 100 units? It is 15 units, that much is increase. So 100 plus 15, that is 115. Just to find out the percentage very easily, we assume original value to be 100 units. Got it? Here, what is the increase in the length by percentage? It is 0.1 percentage. What is 0.1 percentage of 100 units? It is 0.1 units. That much is increase. So 100 plus 0.1, that is 100.1, that many unit. Got it? Put these two values of L1 and L2 here. Find out R1 upon R2. L1 is 100, L2 is 100.1. Find out R2 in terms of R1 from here. You will get it exactly this much. R2 equals to 1.002001 R1. Correct? Now suppose I want R2 minus R1. Okay? What is R2? 1.002001 R1 minus R1 as it is. Come on, take R1, R1 common. Inside the bracket 1.002001 minus 1. Now this minus 1, it will be 0.002001, that many R1. Got it? Now take this R1 in the denominator. Fine. So it is R2 minus R1 upon R1. It will be 0.002001. Now just multiply this by 100 percentage. R2 minus R1 upon R1 multiply by 100 percentage. What will it give to you? Change in any physical quantity divided by its original value multiply by 100 percentage will give you percentage change in that physical quantity. Right now, because you are stretching the wire, length will increase, and correspondingly when length will increase, come on, resistance will increase. So this will give me percentage increase in the resistance, percentage increase in the resistance. Increase in the resistance divided by original value multiply by 100 percentage will give me percentage increase in the resistance. Put up this value. This value is 0.002001 multiplied by 100 percentage. When you multiply by 100 percentage, this decimal point will appear here now, 0.2001, that many percentage. Okay, this is most accurate value, most accurate answer. In textbook, they have adopted the method of derivative, and in that method, they are getting final answer 0.2 percentage. Then you may tell me, sir, 0.2 and 0.2001, they are nearly equal. Yes, it is true. But because the percentage increase in the length is very small, 0.1 percentage, then you could get almost the same answer. But if the percentage increase in the length is very large, say by 35%, then if you adopt the method of derivative given in the textbook, you will be getting answer 35% multiplied by 2. That is what they have written. dr upon r multiplied by 100% is equal to 2 into dl upon l into 100%. So at that time 2 into 35%, you will just write the answer 70%, but that would be very wrong answer. If you find out that answer using this method, then it is not 70%, it is more than that. Okay? So remember, this method is most accurate also and most general method. You can apply it for any change in length, might be very small, might be very large. Okay? Please remember, whenever you stretch any wire uniformly, R is proportional to L square. Remember this relation. So right now final answer is 0.2001, that many percentage, most accurate answer. Okay? Now let me just derive one very important result, because we are going to use it in the next example. In the theoretical part, we had studied about relation between resistivity and temperature for metals. What was the temperature difference of resistivity in case of metals? It was ρ2 equals to ρ1 into bracket 1 plus alpha into theta 2 minus theta 1. Give me identification of each symbol. What is alpha? Temperature coefficient of resistivity. What is ρ1? It is the resistivity at temperature theta 1. What is ρ2? Resistivity at temperature theta 2. Okay? Now I want similar formula in terms of resistance. All that you can do, just put up the values of ρ1 and ρ2. Find out ρ from here. It is R into A upon L. Ρ is R into A upon L. Ρ is R into A upon L. Okay? Because here it is ρ1, which is the resistivity at temperature theta 1. Then here I am writing R1, which is the resistance at temperature theta 1. Because here it is ρ2, which is the resistivity at temperature theta 2. Here I am writing R2, which is the resistance at temperature theta 2. Now from both the sides you can cancel A and L also. Then you will get the relation between R2 and R1 as R2 equals to R1 into bracket 1 plus alpha into theta 2 minus theta 1, correct? What is alpha at that time? Temperature coefficient of resistance. See, the same thing, same alpha you can take as temperature coefficient of resistivity also. These two alpha have got same value and same unit also, okay? So whether you speak out as temperature coefficient of resistivity or temperature coefficient of resistance, it is one and same, okay? This is the resistance at temperature theta 1, this is the resistance at temperature theta 2, okay, fine. Now we will use this equation in the next numerical. Just kindly read this statement of number 6. Read it? Fine. See, in the statement you must have come across two new words for you. First is resistance thermometer. Resistance thermometer. All of you know about thermometer. It is the device with the help of which we can measure the temperature. But resistance thermometer is that thermometer in which first we measure resistance, and from the measured value of resistance we can find out corresponding temperature, okay? That's why it is called resistance thermometer. Resistance thermometer is that device in which firstly resistance is measured, and then using measured value of resistance we can find the temperature. Such a device is called resistance thermometer. Got it? Another word is heat bath. Heat bath means nothing but a liquid which is kept at higher and constant temperature. A liquid which is kept at higher and constant temperature is called heat bath. Okay. Now let us solve this numerical. Just now we have obtained temperature dependence of resistance of a metallic wire. It is given by this formula. R2 equals to R1 into bracket 1 plus alpha into theta 2 minus theta 1. Correct? Come on, take this R1 in the denominator. It will be R2 upon R1. Transfer this 1 will become minus. And now take LCM. R2 minus R1 upon R1. R2 minus R1 upon R1. Right hand side as it is, alpha into theta 2 minus theta 1. Alpha into theta 2 minus theta 1. Give it equation number 1. Fine. Now, first temperature they have given melting point of ice. And you know, at 1 atmospheric pressure, melting point of ice is 0 degree centigrade. So theta 1 I am taking 0 degree centigrade. At that time they have given resistance 5 ohm. Another temperature they have given 100 degree centigrade. Correct? 100 degree centigrade. And at that time resistance is 5.23 ohm. This 100 degree centigrade, you know, it is boiling point of water. Boiling point of water. Okay? At 1 atmospheric pressure. Fine. Now R1 is 5 ohm, R1 is 5 ohm, and R2 is the resistance at this temperature, which is 100 degree centigrade, and the resistance is 5.23 ohm. 100 minus 0, that is 100 into alpha, 100 into alpha. Give it equation number 2. Now here we keep this initial temperature as it is, but final temperature we change from theta 2 to theta 2 dash, and at that new final temperature, the new resistance value I am showing by symbol R2 dash. Okay, this R1 as it is. Fine. Now tell me, what have they given in this statement? At initial temperature, that was melting point of ice 0 degree centigrade, the resistance was 5 ohm. But at new temperature of heat bath, the resistance they have given 5.795 ohm. Okay. Now tell me, theta 2 dash minus 0, that is theta 2 dash into alpha. I have written here theta 2 dash into alpha. Give it equation number 4. Now take the ratio of equation 2 to equation 4. That is, this upon this will be equal to this upon this. Correct? When you take this upon this, 5 will cancel. Correct? 5.23 minus 5, that is 0.23, 5.795 minus 5, that is 0.795, and when you take this upon this, alpha alpha will cancel, giving you 100 upon theta 2 dash, 100 upon theta 2 dash, correct? Simplify this, find out theta 2 dash, answer is 345.65, that many degrees centigrade. So this must be the temperature of heat bath, okay? How much? 345.65, that many degrees centigrade. Why this has come out in degrees centigrade? Because these two temperatures were in degrees centigrade, correct? This was in degrees centigrade, so this must be in degrees centigrade. By chance, if they ask temperature of heat bath in Kelvin, then first answer you will get in degrees centigrade only, but if you want to convert into Kelvin, you can add 273, that everybody knows, okay? At that time, just read the statement carefully, what actually they have asked, and then try to solve accordingly, okay? So this is the temperature of heat bath in degrees centigrade. If asked in Kelvin, you can add 273, got it? Now kindly read this statement of illustrative numerical number 7. Read it? Look. See, in the theoretical part of this chapter, we had obtained this formula d rho upon d theta equals to alpha into rho. Remember that formula? What is d rho by d theta? It is temperature rate of change of resistivity or rate of change of resistivity with respect to temperature. Correct? Fine. And what is alpha? It is temperature coefficient of resistivity, correct? And rho is resistivity, fine. Now, here we are given reference temperature. That reference temperature is 20 degrees centigrade, okay? In the statement they have given. Now, for the first material, you can write this formula as d rho 1 upon d theta equals to alpha 1 into rho 20, outside the bracket you can write 1. What does it mean? This is the rate of change of resistivity of first material with respect to temperature. This is alpha 1, temperature coefficient of resistivity for first material, and this is the resistivity of first material at 20 degrees centigrade temperature. Got it? Similarly, for given second material, you can write the formula like this: d rho 2 upon d theta equals to alpha 2, then into bracket rho 20, outside the bracket you should write 2. Just give me interpretation of each symbol. This is rate of change of resistivity of second material with respect to temperature. This is temperature coefficient of resistivity for second material. This is resistivity of second material at 20 degrees centigrade temperature. Got it? Fine. This equation I have written for first material, and this equation I have written for second material. Okay. Now in the statement they have said that by mixing these two materials, we have prepared one such a mixture whose resistivity does not change with temperature. Correct? And resistivity of that mixture, they have said in the statement, to be taken equal to summation of individual resistivities. Look. Resistivity of first material is rho 1, for second material rho 2, and because they are given in the statement, the resistivity of mixture is equal to summation of resistivities of two materials. I can write mathematically rho equals to rho 1 plus rho 2, correct? That is for mixture. Just take d by d theta on both the sides. D by d theta, that is derivative with respect to temperature. So I am writing here d rho by d theta. Here d rho 1 by d theta plus here d rho 2 by d theta, correct? But what additionally they have said in the statement, we are supposed to prepare one such a mixture whose resistivity must not change with temperature. So, if this resistivity of mixture is to be kept constant with respect to temperature, then d rho by d theta must be taken 0 because this resistivity of the mixture is remaining constant, and anything which is constant, its derivative will be 0, correct. You know derivative of a constant function is 0, correct. So, for mixture rho is constant, and so d rho by d theta must be 0, correct. So, this d rho by d theta is 0. Formula for d rho 1 by d theta is this much, same formula written here, come on, plus d rho 2 by d theta, it is this much, same formula written here, correct. Now, put up the values, 0 as it is. What is alpha 1? Temperature coefficient of resistivity for first material which they have given in the statement, 6 into 10 raised to minus 4 degree centigrade inverse. What is this rho 21? It is resistivity of first material at 20 degree centigrade temperature which they have given 2 into 10 raised to minus 8 ohm into meter, correct. And then this is the temperature coefficient of resistivity for second material which they have given minus 5 into 10 raised to minus 4 degree centigrade inverse. And this is the resistivity of second material at 20 degree centigrade temperature which we are supposed to find out, okay. Just simplify, you will get this value this much, 2.4 into 10 raised to minus 8 ohm into meter, correct. Because the unit of resistivity for first material here, it was ohm into meter, naturally this resistivity will also have same unit ohm into meter, correct. And can you understand one point here? Why the resistivity of mixture has remained constant? Why? What is the reason? Reason is that, have you seen, the temperature coefficient of resistivity for first material is positive and for second material it is negative. So, what does it mean? For first material, when temperature coefficient of resistivity is positive, meaning thereby if temperature will increase, then resistivity of first material will increase. But because temperature coefficient of resistivity for second material is negative, that time when temperature will increase, come on, resistivity of second material will decrease by the same amount. Ultimately, this summation will remain constant. When this will increase, this will decrease, okay. You can just speak opposite, I mean conversely you can say, when this will decrease, this will increase, correct. So, I mean to say rho will remain constant, correct, fine. Come on, read now statement for number 8. Read it, come on. We are given one bulb. When that bulb is off, naturally the filament is cool, correct. When filament is cool, at that time temperature is low. When temperature is low, let it be theta 1. At that time resistance of filament I am taking R1, okay, in the off condition of the bulb. But when you switch it on, that time current is passing through the filament, will raise the temperature of the filament. So, that time temperature will be higher. That higher temperature in the on condition I am taking as theta 2, and at higher temperature resistance also will be higher, let it be R2, correct. So, this is the resistance of the filament of given bulb in the off condition at temperature theta 1 which is low, and this is the resistance of same filament in the on condition of the bulb at higher temperature theta 2, correct, fine. When you apply voltage to the bulb, naturally it will turn on, and in the on condition when you can apply Ohm's law, that is voltage equals to current into resistance, voltage equals to current into resistance. But in the on condition, what is the resistance of the filament? R2, that is why I am writing here R2, correct. Voltage applied equals to current multiplied by resistance, correct. What is the voltage applied in the on condition? 30 volt. Current passing through the filament in the on condition is 0.185 ampere, that is what they are given, and R2 we require, you will get the value 162 ohm, correct. Now tell me, at lower temperature theta 1 resistance is R1, at higher temperature theta 2 resistance is R2. And you know the relation between R2 and R1, that relation is R2 equals to R1 into bracket 1 plus alpha into small bracket theta 2 minus theta 1. Remembered? Come on, put up the values. This is the resistance of filament of a given bulb in the on condition, which we have found out 162 ohm. This is the resistance of filament of the same bulb in the off condition, which they have given in the statement to be 18 ohm. 1 plus as it is, what is alpha? Temperature coefficient of resistance of filament of that bulb, which they have given 4.5 into 10 raised to minus 3 Kelvin inverse or degree centigrade inverse, it will make no difference. Then this higher temperature we require, and the initial temperature, which is low temperature in the off condition, they have given 293 Kelvin. If you are taking this temperature in Kelvin, naturally this also will be obtained in Kelvin. Okay, fine. Now find out theta 2, you will get 2070.7, that many Kelvin. By chance, if they ask the temperature of filament of that bulb in the on condition in degree centigrade, then when you want to convert this temperature from Kelvin to degree centigrade, you should subtract 273 from this value. Got it? Fine. Or otherwise you can do one thing, this temperature you may take degree centigrade, this temperature you may take in degree centigrade, so naturally you will get theta 2 also directly in degree centigrade. Got it? Fine. Don't bother for the unit of alpha, because in the formula of alpha, that in the denominator it appears not temperature but temperature difference. So unit of alpha, there it is used degree centigrade inverse or Kelvin inverse. Both the units are equivalent, because it is not the unit of 1 upon temperature, it is the unit of 1 upon temperature difference. That's why. And you know temperature difference, whether you measure in degree centigrade or in Kelvin, it comes out to be same. Okay. Read now statement for number 9. Read it? Look. Come on. Formula for charging current in case of charging process of lead storage cell. We had derived in the theoretical part. What was that formula? Capital I equals to capital V minus capital E upon capital R plus small r. Same formula written here. I equals to V minus E upon R plus R. Just give me identification of each symbol. This is charging current. Okay. What is this capital V? It is the terminal voltage of DC source connected for the process of charging of a given lead storage cell. Correct? And that terminal voltage is higher than the EMF of the lead storage cell, which is to be charged up. Okay? This is the effective EMF of the lead storage cell, which is to be charged up. What is capital R? Resistance connected in the external part of the circuit in series with lead storage cell. And this small r is effective internal resistance of given lead storage cell. Got it? Come on, put up the values. This terminal voltage of DC source, they have given 110 volt minus as it is. This is the effective EMF. Now actually they have said to charge 6 lead storage cells connected in assisting connection in series. Come on, for an assisting connection in series manner, you know resultant EMF will be summation of individual EMFs, correct? And individual EMF is each having EMF say 2 volt, and such as 6 cells are there in series in assisting connection. So 2 plus 2 plus 2, how many times? 6 times. That's why this effective EMF is 2 into 6, that is 12 volt. Got it? Capital R is the resistance to be connected in the outer part of the circuit in series with lead storage cell, which they have given 46 ohm. What is small r? Effective internal resistance. For one cell internal resistance they have given 0.5 ohm, and such 6 cells are connected in series. So total or effective resistance in series combination, you know it is simple summation of individual resistances. 0.5 plus 0.5, how many times? 6 times. That's why I am writing here 0.5 into 6, correct? Simplify this value, you will get 2 ampere. Got it? Fine. What about electrical power spent? Electrical power spent for the process of charging. That electrical power has the formula V into I. Actually, we had obtained 4 formula for electrical power. Remember, P equals to W upon T, V into I square into R, V square upon R. Remembered? And out of that, right now I am using this formula V into I. Okay? What is V? That is terminal voltage of DC source. They have given 110 volt. I we have found out it is 2 ampere. Correct? 110 into 2 will be 220. SI unit of power is watt. Leave proper gap here. Right? Capital W, don't put any full stop. Okay? What about wasted power? See, power is wasted in the ohmic resistance. And that ohmic resistance is in the outer part of the circuit also, which is capital R, and in the lead storage cell in the form of internal resistance. Correct? And what is the wasted power? That is Julian power. Julian power has got formula current square into resistance. Current square into resistance. Current square into resistance, that is external resistance, plus current square into resistance, which is internal resistance. Okay? This is the power wasted in the external resistance. This is the power wasted in the internal resistance. And that summation will give you total wasted power. Let it be P dash. Invariably, please use different symbol, different than this. Okay? Because this is the power which we are spending, and this is the power which is getting wasted. Both the powers are different. And why same current you are using here? Because capital R and small r, they are in series, and in a series connection, come on, current will be same. That's why here also I, here also I. Got it? I square you can take common. Inside the bracket, capital R plus small r. Put up the values. I value is 2 ampere. I is 2. Capital R is 46 ohm. Capital R is 46 ohm. Plus small r. Small r, remember 0.5 into 6, 0.5 into 6, got it? Simplify, answer is 196 watt, okay? What about difference? They have asked about the difference of power spent and power wasted. That is bigger power minus smaller power. This is the power which is spent, this is the power getting wasted. Come on, P is how much? P is 220. Minus P dash. P dash is 196. The difference comes out to be 24 watt. Now tell me, what happens to this much power? This much power is getting stored in the lead storage cell. So this is the power which is really utilized because it is getting stored. This is the power which is wasted, and this is the power which we are spending. Okay? So whatever is asked in the sum in the textbook, that we have found out. But in the school examination, they may give some extension to the sum. They may ask these values in percentage. And how will you find out percentage? I am showing you. See, some students are very much afraid of finding percentage. Actually, that process is very simple. Try to understand. Look here. Suppose they ask stored power in percentage. How much power is stored in percentage? If you want to find out, just use this formula. Power stored divided by total power spent multiplied by 100%. Stored power divided by total spent power multiplied by 100%. Simple. What is the power stored? It is 24 watt divided by what is total power spent? It is 220 watt multiplied by 100%. Okay? And this comes out to be 10.9%. That is 10.9% of total power spent is getting stored. Okay? Now we go for wasted power in percentage. Wasted power in percentage. What you should do? Amount of power wasted divided by total power spent multiplied by 100%. What is the total power wasted? Total power wasted is how much? 196 watt. Divided by total power spent is 220 watt multiplied by 100%. This comes out to be 89.1%. What does it mean? 89.1% of total power spent is getting wasted in the form of heat. You can say it is getting dissipated, it is wasted like Julian power. Correct? Fine. And now summation of these two must be 100%. that you can check it here. Okay, fine. I have written here extra note. Okay,